So my talk is not about bug fixing, it's about genetically improved Barracuda. So I'm going to give you a brief introduction to Barracuda and then mostly talk about the results. The claim for 100-fold speed up is of course a cheat. The bit of code that we improved is 100 times faster, but it gets diluted by the rest of the code. So overall it's more like a 2 or 3 order improvement. But that was sufficient to convince the owners of Barracuda to actually take on board the genetic improvement, and it's been incorporated in the official release for 10 months now, and during that time it's been downloaded over 1,000 times. It's been taken up by a commercial firm, Lab 7, and it's also in IBM's port of Barracuda. So Barracuda is a DNA analysis tool. It's not desperately large, 8,000 lines of source code. It's essentially a rewrite of a sequential piece of code, BWA, which has been rewritten for NVIDIA GPUs and runs under CUDA, hence the name. And what it essentially does is take hundreds of thousands of short DNA strings. In bioinformatics, these are known as next generation sequences. So they're very short, they're very noisy, and the first process that you actually do is to try and locate the short sequence against the human genome, and thereby build up a jigsaw that refers to your actual sample. And what you want to do is identify small changes in the real data that correspond perhaps to SNPs or genetic defects in the patient. So the way it gets its speed is by processing in parallel hundreds of thousands of short strings on a GPU. So GPUs are going to talk about K20 and K40s, which actually were donated by NVIDIA. So this picture is basically, this is Barracuda that runs on the server, and then this is the part that runs on the GPU. The colors are essentially, blue is a manual change, which I've done. So the principal change is, instead of directing all of the strings through this kernel, which is does a very exact, a very complicated calculation, what happens is the first pass, the data is thread through this kernel, exact match, which works well for the strings that match the human genome exactly. So if a string matches the human genome exactly, this guy will find it in human genome and return that as an exact match, and that will be all that's necessary. If it doesn't match exactly, probably due to noise in the data, then it falls through this switch, which was manually inserted, and goes back to the original, more complicated piece of code. So this one works much faster, but it doesn't give you a full answer. This one is needed about 15% of the time. And what we've done, so that's the manual bit, and then we use GP to improve the stuff in red. And you can see the common code is actually improved, which also improves the more complicated kernel. I'm just going to skip that one. Yeah, so before we run evolution, we do this check about does the code match exactly or not. We've also inserted 15 different options. So one of the things about GPU programming is there are lots of different ways of skinning a cat, and it's far from obvious which is going to be the best. What we've done is insert by hand conditional compilation, so we can actually try different options. or rather the GP can try different options. So, and these options interact. It's not a question of simply choosing the best one and moving on to the next. It is a more complicated search than that. In addition to that, there's searching at the level of changing the code. So what you'll see later is these guys come across as a fixed GA. These ones are more of a traditional GP variable length thing. Those are the parameters. So the way the evolution works is we start with a source code, we create a grammar, and the grammar controls the way the GP works. So we have a population, not a population of code, but a population of patches to the code. The little rectangular bit is the 15 fixed parameters. So that's, if you like, is the GA part, and this is the GP part. But our individual is a composite of a fixed part and a variable length part. We can mutate and cross over the population, create a new population. That creates, using the grammar, different patches. For point of view of speed of compilation, those are all spliced into one file, which is compiled in one go. So we're actually here, we're going to compile 1,000 different programs together. We test them one at a time using examples from the 1000 Genome Project. When we run these examples, we also run the original version of our code. So we have a test. Do we produce the same or at least an equivalent answer as the original code on 150,000 different examples? Do we actually run faster than the original code? If you satisfy both of those, that gives you your breeding population. You take the top 50% of that population and create the next generation. One child is created using mutation, one child is created by crossover. That gives the next population, and then we iterate around this loop 50 times. So this is an example at the top of code, essentially written in C, and you can see here an example. Here we want to actually get data from the sequences array, and it's coded up two very different ways of actually getting it. They produce the same answer. It's far from obvious which of those is going to be the best one. And so what we've done is we've left it to evolution to choose which one. So this conditional compilation switch is actually one of the configuration parameters the GP can tweak. That code is automatically converted into a grammar. The stuff in red is just source code that's transferred, and then you can see there are things like this if, where essentially the part of the if within the round brackets is extracted, and that becomes a separate rule that we can replace with any other if. So any other if within the code will syntactically fit there. It will be syntactically correct. By using scoping rules, we can also almost guarantee that it will compile. There are some exceptions where things don't fail to compile, but about 97% of our mutants not only syntactically correct, but also compile.
Could you say something about the nature of scoping as
well? I think there's a slide on that a bit later, yes. So the grammar, although it's, where are we? 650 rules are fixed, so the GP can't change them. There are about 115 which are variable. Most of those are simple assignment statements. And then there's this example of an if. So again, the round brackets can be transferred. The grammar also takes care of things like for loops, and it inserts into the for loop this macro OK, which is designed to terminate a kernel. So if our loop goes round far too many times, OK suddenly goes false and aborts the loop, probably giving the guy very poor fitness, but at least the kernel stops. What you don't want to do is have to go into the machine room and reboot the thing by hand. So this is a backstop that kills things, prevents them running forever. So the representation, again, as I said before, is the 15 fixed parameters and then a variable list of changes. When we do crossover, we use uniform crossover on the fixed part and something very akin to tree crossover on the variable part. So it's a 2-point crossover on the variable part. Mutation is either we're mutating this guy or we're mutating that one. If we're mutating this, we simply choose one of the 15 and change it. And mutating the code means actually adding another patch. And the patches are basically based on Claire and Chris's ideas. We can delete a line of source code, we can replace a line of the same type, or we can do an insert. So we can copy a line and insert it elsewhere into the kernel. This is an example of, so this is how we represent a mutation. In this case, we're doing an insert mutation. So the plus means we find line 947 and we insert in front of it a copy of line 929. So that's the original, and then here's the result of doing a mutation. Reason for choosing this is it comes up in the solution later on. So this is on the K20, which is the smaller of the two GPUs, the result of evolving for 50 generations. So these are the changes to the fixed part. So we've turned on this particular parameter, and what that means is the BWT cache is going to be kept in registers instead of in shared memory. We're going to use twice as many threads as before, and we also double the size of the block. You can see that those two are strongly influencing each other. If you do one, it probably makes sense to do the other one. So those are the fixed parameter changes. This is the changes to the source code. So one of the changes is to insert this pragma before the for loop on line 635. This is one of the ifs. So what's actually happened on line 578 is an if which was never actually invoked. It's replaced with a 0. So this condition, which could never be true, has been replaced by another one. So in this particular example, that code is entirely equivalent to the original. Neither of them were useful. Here's our insert. So what this complicated thing actually does is overwrite L0. It makes no difference because very few lines later, there's another line which overwrites L0. The last one is a deletion. So what's happened is line 126 has been deleted, and the logic of that is very strange. What actually deleting that line of code does is it disables the software cache. So previous to this, there was a small cache of values that were being currently looked up. So part of the DNA string was stored in a cache controlled by that assignment. By removing that assignment, the cache is disabled. It all works fine. Surprisingly, it's actually faster without the cache than with it. It's entirely unintuitive as to why that is, but that's how the hardware and software interact. That's not something that you would expect to find as a program. But you don't care and you just let evolution run. This is what it discovers. I have ignored Jerry's comment. I thought I had a slide on it. In terms of the scoping rules, what happens is when you do a crossover or a mutation that moves code around, it has a lookup table that says, is this a valid location for this line of code to move to? So the line of code has some variables in it. If I move it elsewhere, are all of those variables still in scope? And it checks that as it does the mutation. If that check fails, then it tries another mutation.
How long is the table created? How and when is that table?
That table's created offline at the same time as the grammar is created. Right, so what we've done is we took 10 data sets from the 1000 Genome Project. These are never used in training the GP. On the K20, the best result was about 1.8 million DNA sequences per second. And on the K40, just over 2 million. And then you see a ratio of about 100 to 1 on the original performance. As I said right at the beginning, that is a cheat because you don't really care about the performance of the kernel. What you care about is the whole machine. But nonetheless, that's sufficient to actually boost the performance of the whole thing. Not only that, in this particular example, the patches produce identical answers to the previous code. And as I say, it was manually incorporated into the release of source George. And the last time I checked, it had been downloaded 1,068 times. I'm going to skip that one. So to conclude, in where it's feasible to do a GI system and you can compile it into one executable, there does seem to be really sizable advantages in compiling a whole lot of small patches together. Here we compile 1,000 patches into one executable. I've just talked about the scoping rules that Jerry raised. In terms of, as I said, there were a few cases where the mutated code didn't always compile. Most of the times it did, and the workaround was simply to run the compiler once, work out which of the patches were not compiling, exclude them, and then run the compiler again. Although that sounds like it has a big overhead, in fact, most errors are reported in the first pass of the compiler, and so the overhead is not so big. The expensive part of the code of the compiler is the code generation, which it only attempts to do after it's detected all the errors. And as I said, on real code overall, sorry, on real test examples overall, we got the speed up of typically between 2 and 3. And that paper is on the archive. Okay, so I mentioned the CEC special session. There's still days and days to write your paper and get it submitted. One thing I didn't mention is there will be at Gecko also in July an issue of the Human Competitive Awards. So I guess here everybody believes that their automated system is competitive with humans. Submit it, get cash prizes. Top prize here is $5,000. Okay. Thank you.